We've been looking at the forces that create a species-rich plant community, and we've looked in some detail at one particular site, looking at the species that emerge as the growth season progresses. So we have an idea of how biodiversity has come about in this community, but of course we're also searching for general phenomena creating biodiversity in other environments, so it's time to take a look at other plant communities and compare them. Essentially, the main question we'll be answering is, why do some communities have more species than others? We've already seen that heterogeneous environments, and in particular sites that are managed in a heterogeneous way, have a larger species pool. But this is only part of the story. To really understand, we need to consider something called productivity. Productivity is an interesting phenomenon because on the one hand it essentially represents the amount of plant growth within the overall vegetation, but as plants grow and become large, they can affect the smaller plants, and so changes in productivity also change the types of plants that can survive, and so the character of the plant community. Technically, productivity is a measure of how much biological material, or biomass, accumulates over a defined period of time. And it's a symptom of how the vegetation works because greater productivity represents greater rates of processes such as photosynthesis in the individual plants. To measure productivity, we need to cut and destroy plots of vegetation at the start and at the end of the growth season and work out the difference in biomass. A less destructive and less time-consuming approach is to simply measure what we call the standing biomass, or the amount of material that is simply standing in place. But we must be careful to do this at the end of the growth season, at the peak of growth. So what we call the peak biomass is correlated with productivity, not in a simple way, not in a linear way, but we can measure peak biomass and use this to directly indicate productivity. So if we do this and relate productivity to the species richness in different herbaceous plant communities, what we get is this. Firstly, the different coloured points represent different types of meadow or pasture grasslands, and the codes stand for classes recognised by European Union law, specifically the so-called Habitats Directive. The grey points are other herbaceous habitats that are not meadows or pastures. These are all real data points that we measured in northern Italy, but the habitat classes are important habitats recognised throughout Europe. So one of the first things to jump out at us is that meadows and pastures are the most species rich and are all characterized by moderately low productivity, whereas communities at extremes of productivity, both extremely low and extremely high, do not have many species. So what's going on here? Well, we've already seen that a species-rich grassland can be characterized by a few dominant species with similar approaches to survival or strategies, but also a much larger range of subordinate species that show a wider range of strategies and functioning. In fact, when we plot a similar graph, but instead of species richness or the number of species, we plot strategy richness or the number of strategy classes in each plant community, we can see that there's also a peak in strategy richness that matches the peak in species richness. So more species because there are more strategies, more ways of surviving. Now, I've not shown it here, but this is also linked to greater variability in specific traits, such as whether the species have soft or tough leaves and so are inherently fast or slow growing, if they tend to spread out, or even the date when they start flowering. So we have variability in the number of strategies, but what about the type and character of these strategies? How do these change along the productivity gradient? And why are only a few species found at extremely low and at extremely high productivity? Well, what happens is very interesting, but I have to put together various pieces of information to explain it properly. First, we can plot each plant community according to the average CSR strategy of the plants that make it up. So in the CSR triangle we've been hearing so much about. This tells us about the general approach to survival that's evident for each community. Then the colour indicates the species richness, so yellower equals more species, dark means very few species. Then the size of the point for each community represents the amount of biomass, indicating the productivity. In this case, larger equals greater biomass and greater productivity. So essentially we can see that species poor communities are either dominated by plants that get large fast in productive situations, which I can tell you are river margins or roadside verges, or species poor communities are characterized by small, extremely fast-growing species in low productivity and highly disturbed situations. Interestingly, lowland meadows have moderate to very high species richness, intermediate productivity, and intermediate competitive ruderal ecological strategies. Calcareous grasslands have the highest species richness and have low to intermediate productivity and intermediate strategies, but this time the strategies are competitive stress tolerators with lower values of ruderalism. Grasslands found over siliceous rock or acid soil have extreme stress tolerator strategies and low to intermediate species richness and productivities. This makes a great deal of sense biologically because the way that plant roots take up nutrients is less effective in acid soils, and there are fewer species that are specialized to cope with this restriction to growth. So coming back to the main graph, the plant communities at the extremes of productivity have small numbers of species for different reasons. Highly productive vegetation occurs where the environment is stable and has plenty of resources, light, water, and soil nutrients, and very few limitations to growth or events that destroy the biomass that's already been produced. The fittest plants in this situation grow large rapidly, and few species can survive underneath them. At low productivities, plant communities are either composed of species adapted to extreme levels of disturbance factors that destroy biomass after it's been produced, or to stress factors that limit growth and biomass production. High species richness is not possible at these extremes, but richness can emerge at low to moderate levels of productivity because it's not absolutely necessary to be highly specialized ecologically in order to survive. Why is this not a simple relationship where all communities at moderate productivity are rich? Why are only some communities at moderate productivity full of species? This is where the species pool comes in. In heterogeneous or patchy environments with a wider range of habitats, a larger number of species are generally found throughout the landscape and can contribute to the richness of each single habitat. Where the environment is more homogeneous and there are fewer species in general, the local richness of each community is restricted. Although the relationship between productivity and species richness is not simple, we can't just take a measurement of biomass and know the species richness. What we can know is where high richness is not possible, and the character of the plant communities that are found along this gradient. This kind of information is fundamental to understanding how environmental changes alter productivity and will restrict or encourage richness. This affects how we can effectively conserve local biodiversity, or where we must pay particular attention to the character of that biodiversity.